tachyonic antitelephone. Well, this is one method that's controversial, and it allows us to call ourselves in the past or somebody else in the past. The consequences of this device would be massive, and it could cause huge problems to causality. Welcome to the Mind Grid, and today we will discuss the device called the tachyonic antitelephone in detail. But before we jump into the actual device, let's look at what causality is and how Einstein's definition of special relativity put together a framework in which we will continue to see how light is the highest speed which is enforced by something in the physics itself. So the key idea here that Einstein proposed was that the universe itself is enforcing the maximum speed on information, light, whatever. The communication itself is bounded by the speed of light. And the way this can be understood is that you can define any inertial frame. And in an inertial frame, when we shoot a beam of light from a given point here, let's say the origin, this light will travel at a 45-degree angle, assuming that this axis, which we are calling time, represents, it's actually c times t. So it represents the distance light would travel in that much time. And this is the x or y axis. And so this always makes a cone of light from this given point. And the key idea that Einstein proposed was that in any inertial frame which is moving at a constant velocity with respect to this original frame, the light speed would always be the same. No matter what speed you pick, as long as that speed is below the speed of light c, this light cone would appear the same. The speed of light would appear the same no matter what speed you pick, which is a very unusual finding. Now, the other thing that comes out of this, these assumptions, is that whatever happens here at this point, which is the origin, it can only affect space-time objects within this cone, and nothing outside this cone can be affected because nothing can travel at speeds faster than light. So within this cone is everything that travels slower than speed of light. At the surface of this cone is points and events that are exactly at the speed of light. Outside this cone, here in this space, and space beyond this cone are points that are beyond your reach, and you have to travel faster than light to be able to reach these points. Now, it is not to confuse that any point in space is accessible. I'm not saying that you can never reach this point. It's just you cannot reach it from this space-time point, which was the origin here. You cannot reach this from this point. You might be able to reach it from this point, and the cone coming out of this might reach that. So every point in space is accessible, but every point in space-time is not accessible to us. That is the great finding. Now, this cone can also be projected downwards, and it similarly shows that the past light cone is the set of events that could have affected this point. So something outside that space-time in the past, for example, could not have impacted this point. And so the critical idea then here, which I have also covered in another video before called the Tolman's paradox, the idea is that that if you try to travel at the speed of light, actually beyond the speed of light, then you would break causality. And I just touched upon half of that idea. We will today cover the other half of the idea, and together, when these two ideas are combined, you will end up making what is called as tachyonic antitelephone, and that allows you to break causality and call yourself in the past, much like, like Marty does in Back to the Future movies. Um, so there is another thought that, there must be some sort of a mechanism in the universe that might prevent us from breaking the timeline and confusing ourselves and confusing the order that we see in life. There must be some sort of other mechanism that once we start breaking the speed of light, you will see problems that we don't foresee yet. But it is definitely a paradox that will emerge as soon as you start having faster than speeds of light for travel. Now, for somebody who grew up watching Star Trek as a child, this idea is kind of hard to grasp because we always assumed that in Star Trek the communication was instantaneous, almost instantaneous across the galaxy, and that's how they could talk so easily, and they could travel obviously at warp speeds. So this was kind of an idea that we thought, or at least I thought, that would be very feasible in the future. But then I hadn't thought about causality and the ramifications of space-time on our events. So that's kind of the key idea. All right, so before we actually describe the device of antitelephone, let's try to comprehend or understand the framework in which we will talk. And so this framework is going to be called the Minkowski diagram. Minkowski is a scientist that came after Einstein. His theory was proposed, this diagram was proposed after Einstein's special theory of relativity, and it kind of helps us understand this framework so that we may make better sense of how objects move and what the impact of those might be. So here in the diagram, we see two kinds of axes. One is the simple x and t axes of the first frame, which apparently is at rest. So it looks pretty straightforward. It looks mostly Galilean. And then we have this other frame in which the axes are kind of tilted, and we call this the x prime frame. And so the idea was that if you start traveling at a velocity, then the frame in which you're operating is going to have to shift its axes in some sort of a transformation so that you can preserve the velocity of light. And this green shaded line represents that light cone that we just described. This light cone represents light traveling at the speed of light, obviously the photonic speed, and this angle is 45 degrees. So in this diagram, there are these special characteristics that, whatever frame of reference you will use, it should honor the speed of light. So that's why there are these 45-degree lines that represent the light cone from the origin. And then you see one more frame. So now let's describe the experiment. So the experiment is we will send a message 1 second away at the speed of 0.5 c. Now, when the message is received at the target, the time in the original frame, the xt frame, is going to be 1 second. Obviously, that's the premise. And it's going to be 1 second, and the distance traveled at, if you send the message, which we will speed up to FTL, but at this point it's only half the velocity of light, it will reach the distance of 0.5 here on this axis, right? In 1 second, it will reach 0.5 c. So that point is 0. And this is all distances in c, so 0.5 c. And this is the point. And this is the point here on this on this diagram, but this is in the xt frame. Now, what we do is that once we are given this, and once we are given our x prime and t prime axes in that moving object, which is traveling at half a speed of light, right? So first of all, the signal is being sent at half the speed of light towards this. It's like a beam that's shot in this direction, which arrives here at this point. And then we want to see how this event is seen by the other ship, which is traveling at half the speed of light, and what would be the coordinates x prime and t prime of this original x and t. So in other words, you know that in special relativity, lengths will contract and time will dilate, and x prime and t prime will not be the same as x and t, because the frame of reference, which is the ship, is moving. And from twin paradox, we also know that, you know, my twin who is traveling in a spaceship will experience time such a way that he remains younger when he gets back to Earth, where I am. So based on that, we can always calculate the x prime and t prime. And for this, you can use the Lorentz equations, or you can use this Minkowski diagram. Either way is fine. Normally, when you have a point, the way you find x prime and t prime, given any point like this point here, what you have to do is you have to draw two parallel lines, one parallel to the x prime axis. So if you do this, it cuts the red axis here. So this is the t prime, and t prime we have calculated here is 0.87. This calculation we have done based on the Lorentz transform equations. So we already know that this is the t prime here. The other thing is what is the x prime. So if you draw a line parallel in this direction, and then you will see that it will intersect exactly at 0. So we know that x prime is 0. So this event lies at t prime equals 0.87 and x prime equals 0, which means it lies at the origin at time 0.87. Now we know that from the perspective of the twin that is on Earth and not moving, this point looks like it's at 1 second and it's at 0.5 c distance. But to the twin that is moving in the airplane, in the spaceship, it looks like this event occurs at origin, and it occurs at time equals 0.87 seconds. So there is a discrepancy, and this is basically what in relativity is called the relativity of simultaneity, right? So what occurs at the same time is not really the same time for something else, right? So what is happening in one frame of reference may not be the same, but both frames must measure the velocity of light to be the same. So now let's carry on forward. Now that we have established that the time measured in the first frame was 1 second, but the time measured in the second frame, which was moving at velocity 0.5 c, and it was trying to measure a signal that was being shot at 0.5 c, was 0.87. So it contracted a little bit, but this is still okay. This is still, I guess, relatively straightforward to understand in relativity terms. So now let's move forward. Now, when we shoot this signal at 1 c and apply the same stuff, so now we see that this point, which is at 1 second later, and it's exactly 1 c distance, this now falls on this light cone, this null vector. This point lies on that, and at this point, when you measure the x prime and t prime, now the t prime is a little bit less, and t prime is 0.58 seconds, right? So it is beginning to decrease more and more as we speed up. Next, we speed up to 1.5 c. If we speed up to 1.5 c, we have gone past this light cone, and now this point lies here. And if we calculate this point's x prime and t prime, which is what it will look in my cousins who's traveling in this spaceship at half the velocity of light, what does this point appear in that frame? And you will see that in that frame, my cousin's clock would be showing 0.29 seconds, my clock would be showing 1 second. So it's slowly going further and further away, and now finally, when we align this point at 2C, we are now sending our message using some sort of a tachyonic device that can send the signals twice the speed of light. At that kind of velocity, we see that this point lies here. And when you calculate this in my cousin's time frame, it occurred at time equals 0. In my frame of reference, it occurred at time equals 1. My cousin's, it occurred at time equals 0. So it occurred right there, right? So that's already kind of getting weird that this point is moved in my cousin's time frame just because the speed of signal was at FTL and it was pretty fast at 2C. Now let's just keep going further. At the point equals 2.5C, this is going so fast we have crossed the light more than 2 times its speed. At this point we are outside of our axes. Now notice that this axis of T prime and X prime, this point is now even outside those two axes, right? These were the axes that we had drawn for my cousin, and now we have kind of gone past that axis itself, and now we are outside this axis. Now when you calculate the T prime for this, that T prime is actually negative. You can't see the negative here, but this T prime is now negative, and that is going backwards in time, right? So we are, the signal originated at origin, but this point when viewed from my cousin's spaceship looks like this point originated somewhere before. It originated somewhere before it was sent, right? So this idea is kind of what we will latch on to, that a signal that was sent at such a high velocity, at FTL velocities, especially FTL velocities of a certain kind, that it even crossed the reference frame of the spaceship. The axes, the positive axes of the spaceship, at that point, at that special speed, that there is a major violation. And this violation, what it causes is the time goes negative for my cousin. So in my cousin's spaceship, he thinks that the signal was, to him, it was received before it was even sent. And so causality has been broken at this moment, right? So now that causality has been broken, and we have understood that this was a combination of sending a signal at very high speed and then it being received by a moving object that was traveling not at the speed of light, but it was traveling below the speed of light. So let's say a spaceship is traveling sub-warp, right? It's traveling below the speed of light, but yet the message or the communication system was tachyonic. It was traveling faster than speed of light, and that caused this time to go backwards. So now that is the premise on which we can build our tachyonic antitelephone. Now, tachyon comes from the Greek tachus, which means swift. So there's two other kinds of particles, the luxons, which move at the speed of light, like photons, and bradyons, which move slower than light. And both of these particles are known to exist. The one that is not known to exist and hypothetical, and maybe we can say that it has mass which is imaginary, and it's imaginary particle, the tachyon is faster than light. So if we could have a tachyon, we could make a tachyonic antitelephone. So let's take a look at a tachyonic antitelephone device in action, how we would achieve it. Now I'm not going to show you how to build tachyons, but I would just assume that a tachyon exists, and if it exists and we can shoot it, then let's make a device called the antitelephone. So in this case, the example here will show you that at time t equals 0, Bob's spaceship and Alice, they're both crossing this origin point, t equals 0, x equals 0. Both of them are at the same place, Earth, and they synchronize their clocks. And now Bob's ship is going in this direction at 0.8 times the velocity of light. That 0.8 c is how he passes the point on Earth where Alice synchronizes the clock with him. And the other thing I would like to point out is, like in the previous slides, we should always remember that these are the Lorentz transform equations. Now we can draw our axes, but these equations will help us figure out that if we know the coordinates of x and t in Alice's frame, let's say there's a point here, or there's a point here, or there's a point here, somewhere in this frame, there's a point that Alice knows. Alice can say, okay, here's a x and t coordinate of a point or of an event in my frame. Then these equations can be simply used to calculate what that event would look like. And we also saw that the way to do this is, given a point, you can just draw parallel lines like this point. So if I draw a line parallel to this, I could figure out here the x-intercept, and likewise with parallel line to this. So if I draw a parallel line to this, I could figure out what the t-intercept is. So that would give me what the x and t-intercepts, x prime and t prime intercepts are for this event, and therefore I can figure this out. So, but we will use these equations in short to figure out that, that whatever the ramifications of sending something between Alice and Bob, what would be the x prime and t prime, and those would help us understand what really happens in these frames. So now that Bob has passed, time now is 300 days past the point where both synchronize their clocks. Bob has traveled quite a bit distance further away from Alice. Alice now sends a message saying stockoflight.com has shot up by 10%. So she sees that in the stock market, light.com is a company, its stock is shooting up and it's shot up by 10%. She sends this message to Uncle Bob, and Bob has reached how much? Because Bob was traveling at 0.8 times the speed of light in this direction, he is now at this point, 0.8 times 300 times the speed of light. So if this is 300 days, for Alice, it's simply 300 days since Bob left. So the point, the event that she's talking about, that she shoots this beam of tachyons, the tachyon emitter, that is here, that point is here. She shoots this, but then Bob is further away from her, and therefore 0.8 times c is Bob's speed, and 300 days has passed. So Bob is somewhere here on the x-axis for Alice, and his distance would be 0.8 times 300 days, and this is 0.8 times c because he's traveling at that much speed. So this is Bob's current position, right? This is somewhere along this x-axis. Bob is somewhere along. And the other thing that Alice uses is the speed of the velocity at which she sends this signal is 2.4 times the velocity of light, right? So she sends this tachyonic emitter at 2.4 times the velocity of light, and so that is being shot towards Bob. So keep that in mind. 300 days she shoots this tachyonic beam towards Bob, says light.com stock is up by 10%. Now at 300 days she had shot it, but in another 150 days, so from Alice's perspective, day is now 450 days since Bob left in his spaceship, and then Bob has received the message. So now let's take a look. Bob had already been flying for 300 days in space, and then we shot the tachyonic message emitter. And so for the tachyonic signal, we know that it's 2.4 times the speed of light, and then Bob, who was already at slight distance, so he was moving at 0.8 times the velocity of light, and it's 450 days, so total distance he has traveled is 360 light days, and the tachyonic signal has also now traveled because it was sent at 2.4 times the speed of light, and it has only traveled 150 days because it was shot at 300 days. So at day 450, it's been traveling for 150 days. So total distance traveled by both of them is 360 light days, and that's where they meet. And so at 360 light days from Alice's frame, that's the distance at which the tachyonic signal will reach Bob, and then the the time on her clock says 450 days since Bob left. And remember that she had shot this signal at 300, and she knows that Bob received it at 450, right? So now that we know that in Alice's frame, we can now calculate in Bob's frame using these equations, because remember that Lorentz transform equations need both time and x in one coordinate, and it can transfer this information into the cousin's, or in this case Bob's, spaceship coordinates. And then those x prime and t prime you can calculate by plugging these x and t values and the velocity of Bob's ship. You will get that in Bob's ship the clock is reading 270 days, and Bob's x coordinate for that event is 0. So Bob is seeing that the event at which he gets the tachyonic signal is at x prime equals 0, and at 270 days his clock is reading 270 days, and he is at the origin, and his origin is where Bob is. So essentially Bob's reference frame, the signal gets to Bob, therefore the x prime will be 0, and it has taken 270 days, and at 270 days Bob has received the signal, right? Now that is Bob's reference frame, and we think that Bob's clocks are running slower because he's moving at half the velocity of light. So all this is fine. It's a little bit weird, but okay. Bob received the signal at 270 days. Now let's keep going forward. Now Bob, as soon as at 270 days, Bob receives the signal. He shoots the signal back to Alice, and he transmits back saying the same message he transmits back to Alice, right? So original message was sent at 300 days. At 450 days in Alice's frame, she thinks that Bob received it. In Bob's ship, the clock is only 270 days, and so Bob now transmits the signal back, and as he transmits the signal back to Alice, Alice now is moving. So in Bob's reference frame, the ship is standing still, Alice is moving backwards, right? Just like a train leaving a platform, you can see the platform is moving backwards. You're standing still. So from Bob's reference frame, his ship is standing still, Alice is moving backwards. So if we transform this like this, so at 270 days, so you know that Bob sent it at 270 days backwards to Alice. Alice now is moving backwards, so we can transform her axis this way, and now we will calculate this in Bob's reference frame. So the tachyon signal for Alice will catch up to Alice in another 135 days. So another 135 days plus 135 days, that is day 405 in Bob's clock. That's where it'll catch up with Alice, and that is because Bob shoots the same tachyonic signal at 2.4 times the speed of light. It takes 135 days. The distance on Alice's clock and Bob's clock is 325. That the distance is 324 light days. So you can see that is here. So because both of them have traveled the same distance, light beam, the tachyon beam, has caught up to Alice. So now we have the two coordinates that, you know, Alice and the tachyon beam are 324 light days away from Bob. That is the x coordinate, and the time is 405 days. So that is what we have in Bob's reference frame, right? So now we must, because Alice is moving backwards in Bob's reference frame, let's calculate what we will see the t prime to be. So we apply this equation, and Alice is moving at minus 0.8 c times the speed of light, and the distance traveled is 324 light days, and it was noticed in Bob's reference frame at 405 days. So once we plug in the x and the t and the v into this t prime equation, we get 243 days. So what has happened is that Bob thinks Alice's clock would now be reading 243 days since he left from Earth. And we know that Alice had sent this message on day 300. So the fact that Bob thinks that Alice will now receive this message at day 243, this is kind of weird. This is kind of weird because it says, that she has received this information that light.com stock to jump by 10%. This is 57 days into the past, and she hasn't even sent this message yet because she was supposed to send this message at day 300. And so now the fact that she has this information and she knows beforehand that the stock is going to jump up by 10% in 57 days in future, she can buy the stock and make the money off of the stock. So that idea that we have managed to send a signal back in time to ourselves by reflecting it through Bob's ship, and therefore we have kind of known that information before we even sent it, this is kind of a paradox. And so that is the gist of the tachyonic antitelephone system, right? The system consists of us shooting a beam of tachyons much faster than the speed of light, reflecting this message off of some traveler that is traveling less than the speed of light. And then when that message is reflected back to us, it has actually traveled back in time before it was even sent to us. And using these equations, we can say that we have managed to create a tachyonic antitelephone. Right? Now, the tachyons are imaginary particles. It's not proven that they really exist. And we think that they will not exist because if they did exist, then there would be a paradox. This is clearly a paradox. Now, I've also made another video that says Tolman's paradox, and you can go see that video as well. But that video kind of just shows a much more straightforward way of looking at Tolman's paradox. This video actually uses that Tolman's paradox to build a tachyonic antitelephone device and prove that if you apply Lorentz transform equations, you will end up in a situation where you have received the message clearly before you transmitted it, and therefore you have a clear paradox. So if you have been with me all this time, then hopefully you may have understood what I was trying to explain here, and if you enjoyed it, give me a thumbs up. If you have concerns or questions, you leave me in the comments, and I'll see you in another video very soon. Until then, take care and do not travel faster than light. Bye guys.